This video shows examples 5 and 8 from chapter 2.
Okay, we'll start with example number 5. Let's see. Okay, example number 5 is the locomotive running along a track. It's going to hit a buffer at the end of the track. That's what that EOD stands for. It's meant to be end of track. Okay, by a spring damper system. So that's my spring damper system. I've got a K, spring stiffness K, damping of C, and the mass of the locomotive is M. And we know that M is 2,000 kilograms. K, it says it's 40 newtons per millimetre. Okay, that means it's 40,000 newtons per metre. And the C, although I said in the notes is 15 newton seconds per metre, that should have been 15 seconds per millimetre, newton seconds per millimetre, and so that's going to be 15 times 10 to the 3 newton seconds per metre. Okay, so there's, like I said, the small mistake in the notes. C is 15 newton seconds per millimetre is what it should say. Now we've been asked to find x of t. What's x of t? Yeah. Yes. Now there are a couple of ways we can solve this. Okay, there's an easy way and a hard way. I shall do both, because they're both just as valid as each other. One of them involves using in the alternative form, the other one doesn't. So let's do it the easy way first. If you remember in the notes, we had, when looking at initial conditions, we had this equation. E we had that as our equation. And that is in the notes, I promise you, it's on page 31. And this solution is a solution that will allow you to find the answer just by sticking in your initial conditions. Now we're given initial conditions, we've been told that the train is travelling, x dot, is 10 metres per second. And we can assume that the train hits the buffers at that speed. Okay?
C must not be like 15 newtons per meter.
Sorry?
15 times 10 to the 3.
Yeah, no, indeed. I told you there's a mistake in the notes. It should be 15 newton seconds per millimetre. Okay, in the question. That's why it's 10 to the 3 up here. Sorry? Sine omega dt, yes. This is on page 31 of the notes. It's the last equation on that page. Okay. We know x dot 0 is 10 meters per second. We also know that at this point, x dot 0 equals 0, okay? So we can assume that there's 0 displacement at time equals 0, but a velocity of 10 meters per second. But there's a few other things we need to know. We need to know omega naught, that's in there. We need to know zeta, and we need to know omega d. So let's find omega naught. Square root of k divided by m. And that comes out as the square root of 40 times 10 to the 3 divided by 2 times 10 to the 3. .472 radians per second. Find zeta. That's going to be C divided by C critical, that's C over 2 root mk. So that's 15 times by 10 to the 3 divided by 2, square root of 2 times 10 to the 3, 40 times 10 to the 3. And if you do the sums with that, you get 0.8385. Now, because we have omega naught and zeta, we can therefore find omega d, the damped natural frequency. Omega d, using the equation in the alternative form, omega naught 1 minus zeta squared. So that's 4.472 square root of 1 minus 0.8385 squared. And if you do the sums on the calculator, 2.4367 radians per second. So we have everything in that equation now. We have omega naught, which is in the exponential there, and also in the term in front of the sign. We've got zeta, which we found, and we also have omega d, which is a function of zeta and omega naught. And so we can stick everything in the equation. We know x naught and we know x dot naught, they're 0, so we know that xt equals E minus zeta, so that's 0.8385 times by omega naught, 4.472 T. Well, x naught we know is 0, so that cosine term just disappears. We don't need to worry about it, but we have, over here we've got an x dot naught, which isn't 0. This term, x naught is 0, and so we have x dot naught over omega d, x dot naught over omega d, times by sine omega d t. Now we know that that's 10, and that we know is 2.4367, as is that. And so we can write this out in full. E, that comes out, those two multiplied out to be 3.75 T, times by 4, was it 0.104 sine 2.4367 t. Okay? That equals, I suppose it's write it in a more standard form, amplitude, decaying exponential, oscillation. Okay, there's our solution. So by using this form of the equation at the top up here, since we were given x naught and x dot naught, and we've been given enough information to find omega naught, zeta and omega d, we can just find those values and plug them in and we end up with the solution. Okay? Doing all the sums for these sections here, you get this. And then to rewrite it, I've just taken the 4.104 out of the brackets, okay, to make it in a sort of more standard form. Amplitude, decaying exponential, oscillation, or sinusoid. I said there was an easy way and a hard way. That was the easy way. The slightly harder way, it's not that hard. We know that with a forced a damped free system, the equation for x of t is a cosine. No, it's not that, is it? Apologies. A e to the minus zeta omega naught t cosine omega d t plus alpha. So that's for a free damped system. And the other way to solve this is to find the first derivative of this equation and then solve for the initial conditions. We know that when x is 0, so in this first case, x of 0, we know that equals 0, and that's going to be a. E to the power of 0 is 1. Cosine omega dt is 0, so it's going to be a cosine alpha equals 0. A cannot be 0, otherwise there'd be no amplitude, so cosine alpha must be 0. Therefore alpha, inverse cosine of 0, has got to be pi divided by 2, or 3 pi by 2, or 5 by 2. But let's assume it's pi by 2. So there's alpha for this equation. We need to find a though. And to find a, we must take the first derivative. X dot t, well we have a e to the minus, okay, and then that's multiplied by minus zeta omega naught cosine omega d t plus phi. So that's the first part. Then we have a minus sign, omega d sine omega d t plus alpha. Okay, that line there is the derivative of the equation there. Okay, a is a constant, so that just comes down. E to the minus zeta omega naught t. Well, we have a minus zeta omega naught t that comes out, but we end up with the exponential still there. That's multiplied by cosine omega dt plus alpha. But then obviously the cosine term has to be integrated as well. And so you end up with the minus omega d sine omega dt plus alpha. Now we know x dot of 0, that's going to be a. This term drops to 1 minus cosine alpha minus omega d sine alpha. Now we found alpha. That's pi upon 2. Cosine of pi upon 2 is 0. So that term, 0. Sine of pi upon 2 we know is 1. And so that term is 1. So now with x dot 0 is a times by minus omega d, and then we know that equals 10 meters per second. So therefore a must be minus omega d divided by 10. So that's minus 2.4367 divided by 10. So that comes out to be minus 4.104. That's the other way up, sorry. Yep, that's the other way up. Apologies, guys. A is 10 divided by minus omega d, which is 10 divided by minus 2.4367. It's going to be minus 4.104. So now we know a and alpha, we can plug that into our equation. X of t minus 4.104 e to the minus, and then we can use these values up here. We end up with 3.75 t cosine 2.4367 t plus pi upon 2. Now that is also a valid solution. But you're probably thinking, hold on, that doesn't look anything like what I've got up there. And you'd be right, it doesn't look anything like it, but I can assure you it's the same thing. And let me show you that it's the same thing. Both of those would be valid solutions. Okay, we all there? We have one solution up the top there, 4.104 e to the minus 3.75 t times by sine of omega dt. Down here we've got minus 4.104, so a negative amplitude to start with, which is a bit weird, e to the minus 3.75 t times by cosine of 2.4367 t plus pi by 2. And I'm going to show you now that they're actually equivalent to each other. Now we know from trigonometry that cosine of minus x equals cosine of x, and that's because cosine is what's known as an even function. Okay? If you think about the cosine curve, here's cosine, that's 0. is x. I'm just that's when x is greater than 0. And obviously when x is less than 0, it just continues on. And notice that if I've got a value of x here, say, whatever, I've got a value here, if I take minus x, it's the same value. Okay? So that means that cosine of x equals cosine of minus x. Okay? Now, because that's the case, I can rewrite this equation. X of t equals minus 4.104 e to the minus 3.75 t cosine of minus 2.4367 t minus pi over 2. Now we also know on page 11 of your notes that cosine of theta minus pi by 2 equals sine of theta. Okay? That's just another trigonometric identity. If this whole thing is shifted over by pi by 2 in this direction, so minus, obviously this point goes to there, you end up with sine, the sine function. And so, we notice we've got a minus sine by theta here, so we can say now that x of t is minus 4.104 e to the minus 3.75 t sine of minus 2.4367 t. We're getting close. We're getting close. We've got the sine. And we've got rid of that alpha term. But we've still got a couple of problems. We've still got a minus sign here and a minus sign in there to match what we had before. Well, again, trigonometry, we know that sine of minus x is minus sine of x. And that's because sine is an odd function. Okay, if you did the same math sort of thing here, we'll talk about odd and even functions at a later point in more detail, because it applies when we're dealing with Fourier series. X. Sorry, that's x. This is no. I'll call that t. Okay, cosine. Sorry, cosine looks like this. Sine. Looks like this, and so on. And so if you take a value of minus t here, that's it down here, so t is up here, about there. And so sine of minus t equals minus sine of t, because obviously sine of t is up here, you take the minus sign, you're back down there again, okay? And so we can therefore plug that in here, x of t, the minus obviously cancels with this minus, so we end up with 4.104 e to the minus 3.75 t sine, and obviously that goes 4367 t. And that's exactly what we had from the previous solution. Sorry. So you can see this is the solution we had using the alternative form, which is up here, this method up here. Using that equation, we ended up with this solution. Yep. If we use this method, where we just have this equation, we take the first derivative of it, there, okay, plug in the numbers, we get this is the solution. But then by using a bunch of trig identities and some knowledge and a bit of manipulation, you can end up turning that equation, which isn't the same as the one up here. It produces the same graph, but it's not the same equation. We can turn that equation into that equation, which is the same, okay? Just by using a bit of manipulation and a bit of cleverness. Both, just so you know, both that one and that one would be valid answers, okay? I'm not expecting you to go through and put it in that form. That's nicer than that, but that's fine. Now, question 8 is what I'm going to do next. It says a mass spring damper system is excited by a harmonic force. The amplitude is found to be 20 millimeters at resonance and 10 millimeters at a frequency of 0.75 resonance. Okay. Find the damping ratio of the system. So we've got a system where at omega equals omega naught, A is 20 millimeters, and at omega equals 0.75 omega naught, A is 10 millimeters. So for this case, when omega equals omega naught, we have R, omega over omega naught equals 1. And here we've got R equals 0.75 omega naught divided by omega naught, so R must be 0.75. Frequency ratios. So we've got amplitudes and frequency ratios. Well, we know there's an equation in our notes that caters to those things. Remember, on page, this is equation 2.48. A equals F naught upon K, so that's the static displacement, (1 minus R squared plus 2 zeta R squared. And we've got A for when R equals 1. And we've got A for when R equals 0.75. So it's just a matter of plugging in some numbers. We know that when R equals 1, we have A equals F naught. I'll put R equals 1 down here. It's F naught upon K times by 1 divided by, well, 1 minus 1 is 0. So that disappears. We have 2 zeta R squared, square rooted, so that's just going to be 2 zeta. R is 1, so we don't need to worry about that. So we can find F0 upon K, that's static displacement. Let's go and rearrange this. F0 upon K equals A, when R equals 1, times by 2 zeta. So we have 20 times 10 to the minus 3 times by 2 times by zeta, which is what we're trying to find. So that equals 40 times 10 to the minus 3 zeta. Now A for R equals 0.75 is F0 upon K, 1 divided by 1 minus 0.75 squared plus 2 zeta 0.75 squared, square rooted. We've gotten a value of F0 divided by K, it's there, in terms of zeta. So we can plug that into this equation. And if I divide both sides by that, then I can end up with A R 0.75 divided by F0 upon K. We know that that is going to be 10 millimeters, so 10 So let's do some sums. So if we reciprocate the whole lot and square it all, we've got, this is going to be 4 zeta squared equals 0.1914 plus 2.25 zeta squared Okay, 0.118 is the solution. So we found out the amplitude for when R is 1, okay, in terms of zeta. And we can find from that the static displacement F0 upon K for when R is 1. The amplitude when R is 0.75 involves F0 upon K, the static displacement. And obviously, this case R is 0.75, so we plugged R equals 0.75 into the equation, and we use the F0 upon K we found previously, because static displacement doesn't change. It's when omega is 0, okay? And R is 0. So we plug them in, and we do some manipulation and some summing and some calculations, and you end up going through the motions to find that zeta is 0.118. So it's an underdamped system.